atoms and include a variety of other anions such as Cl, SO24, and S22. Buta otherwise similar to the feldspars. 71. Other inorganic compounds. Silicon disulfide, Cis2, is formed by burning silicon in gaseous sulfur at 100 degrees Celsius. Sublimation of the resulting compound in nitrogen results in white, flexible long fibers reminiscent of asbestos with a structure similar to W silica. This melts at 1090 degrees Celsius and sublimes at 1250 degrees Celsius. At high temperature and pressure this transforms to a crystal structure analogous to cristobalite. However, Cis2 lacks the variety of structures of SO2, and quickly hydrolyzes to silica and hydrogen sulfide. It is also ammonalized quickly and completely by liquid ammonia as follows to form an imide SAD smiley 58, Cis2 plus 4NH3 Cy, NH. 2 plus 2 NH4 shit reacts with the sulfides of sodium, magnesium, aluminium, and iron to form metal thiosilicates. Reaction with ethanol results in tetrethylsilicate SiO8, 4 and hydrogen sulfide. Ethyl silicate is useful as its controlled hydrolysis produces adhesive or film-like forms of silica. Reacting hydrogen sulfide with silicon tetrahalides yields silicon thiahalides such as SiCl3, cyclic Cl2 Si-S2 SiCl2, and crystalline Cis2, 4. Despite the double bond rule, stable organosilicons RSI equals S have been made thanks to the stabilizing mechanism of intermolecular coordination via an amine group. 76. Silicon nitride, Si3N4, may be formed by directly reacting silicon with nitrogen above 1300 degrees Celsius, but a more economical means of production is by heating silica and coke in a stream of nitrogen and hydrogen gas at 1500 degrees C. It would make a promising ceramic if not for the difficulty of working with and sintering it chemically. It is near totally inert, and even above 1000 degrees Celsius it keeps its strength, shape, and continues to persistent to wear and corrosion. It is very hard, 9 on the Mohs hardness scale, dissociates only at 1900 degree Cat1 atom, and is quite dense. Density 3.185 g/cm3, because of its compact structure similar to that of phenacite, B2SiO4. A similar refractory material is Si2N2O, formed by heating silicon and silica at 1450 degrees C in an argon stream containing 5% nitrogen gas, involving 4-coordinate silicon and 3-coordinate nitrogen alternating in puckered hexagonal tilings interlinked by nonlinear SiO-Si linkages to each at a dot. 76. Reacting silyl halides with ammonia or alkylammonia derivatives in the gaseous phase or in ethanolic solution produces various volatile silylamides, which are silicon analogues of the amines SAD smiley 76, 3-SiH3Cl plus 4. NH3N, SiH3, 3 plus 3 NH4 COSI3Br plus 2 Me2 NH SiH3 NMe2 plus Me2 NH2Br 4 SiH3I plus 5 N2H4, SiH3, 2 NN, SiH3, 2 plus 4 N2H5 Many such compounds have been prepared, the only known restriction being that the nitrogen is always tertiary, and species containing the SiHNH group are unstable at room temperature. The stoichiometry around the nitrogen atom in compounds such as N-SiH3, 3 is planar, which has been attributed to a p-d interaction between a lone pair on nitrogen and an empty d orbital on silicon. Similarly, tricylilamines are weaker as ligands than their carbon analogues, the tertiary amines, although substitution of some SiH3 groups by CH3 groups mitigates this weakness. For example, N-SiH3, 3 does not form an adduct with BH3 at all, while Men-SiH3, 2 and Me2 and C3 form adducts at low temperatures that decompose upon warming. Some silicon analogues of imines, with a psi equals N double bond, are known. The first found was but 2 psi equals N psi but 3, which was discovered in 1986. 76. Silicon carbide, SiC, was first made by Edward Goodrich Aitchison in 1891, who named it carborundum to reference its intermediate hardness and abrasive power between diamond, an allotrope of carbon, and corundum, aluminium oxide. He soon founded a company to manufacture it, and today about 1 million tons are reproduced each year. 77. Silicon carbide exists in about 250 crystalline forms. 78. The polymorphism of SiC is characterized by a large family of similar crystalline structures called polytypes. They are variations of the same chemical compound that are identical in 2 dimensions and differ in the third. Thus they can be viewed as layers stacked in a certain sequence. 79. It is made industrially by reduction of quartz sand with excess coke or anthracite at 2500 degrees C in an electric furnace. 77. SiO2 plus 2C Si plus 2CO Si and C. It is the most thermally stable binary silicon compound, only decomposing through loss of silicon starting from around 2700 degrees Celsius. It is resistant to most aqueous acids, phosphoric acid being an exception. It forms a protective layer of silicon dioxide on the surface and hence only oxidizes appreciably in air above 1000 degrees C. Removal of this layer by molten hydroxides or carbonates leads to quick oxidation. Silicon carbide is rapidly attacked by chlorine gas, which forms SiCl4 and carbon at 100 degrees Celsius and SiCl4 and CCl4 at 1000 degrees Celsius. It is mostly used as an abrasive and a refractory material, as it is chemically stable and very strong, and it fractures to form a very sharp cutting edge. It is also useful as an intrinsic semiconductor, as well as an extrinsic semiconductor upon being doped. 77. In its diamond-like behavior it serves as an illustration of the chemical similarity between carbon and silicon. 80. Organosilicon compounds. A hydrosilylation reaction, in which Si-H is added to an unsaturated substrate because the Si-C bond is close in strength to the C-C bond. Organosilicon compounds tend to be markedly thermally and chemically stable. For example, tetraphenylsilane, Si-pH4, may be distilled in air even at its boiling point of 428 degrees Celsius, and so may its substituted derivatives pH3 SiCl and pH2 SiCl2, which boil at 378 degrees Celsius and 305 degrees C respectively. Furthermore, since carbon and silicon are chemical congeners, organosilicon chemistry shows some significant similarities with carbon chemistry, for example in the propensity of such compounds for catenation and forming multiple bonds. 80. However, significant differences also arise, since silicon is more electropositive than carbon. Bonds to more electronegative elements are generally stronger with silicon than with carbon and vice versa. Thus the Si-F bond is significantly stronger than even the CF bond and is one of the strongest single bonds, while the Si-H bond is much weaker than the CH bond and is readily broken. Furthermore, the ability of silicon to expand its octet is not shared by carbon, and hence some organosilicon reactions have no organic analogues. For example, nucleophilic attack on silicon does not proceed by the SN2 or SN1 processes, but instead goes through a negatively charged true pentacoordinate intermediate and appears like a substitution at a hindered tertiary atom. This works for silicon, unlike for carbon, because the Long Cy-C bonds reduce the steric hindrance and the d orbital of silicon is geometrically unconstrained for a nucleophilic attack, unlike for example a CO sigma asterisk antibonding orbital. Nevertheless, despite these C differences, the mechanism is still often called SN2 at silicon for simplicity. 81. One of the most useful silicon-containing groups is trimethylsilyl Me3-Si. The Cy-C bond connecting it to the rest of the molecule is reasonably strong, allowing it to remain while the rest of the molecule undergoes reactions, but is not so strong that it cannot be removed specifically when needed, for example by fluoride ion, which is a very weak nucleophile for carbon compounds but a very strong one for organosilicon compounds. It may be compared to acidic protons, while trimethyl methyl is removed by hard nucleophiles instead of bases. Both removals usually promote elimination. As a general rule, while saturated carbon is best attacked by nucleophiles that are neutral compounds, those based on nonmetals far down on the periodic table, for example sulfur, selenium, or iodine, or even both, silicon is best attacked by charged nucleophiles, particularly those involving such highly electronegative nonmetals as oxygen, fluorine, or chlorine. For example, enolates react at the carbon in halolcanes, but at the oxygen in silyl chlorides, and when trimethylsilyl is removed from an organic molecule using hydroxide as a nucleophile, the product of reaction is not the silanol as one would expect from using carbon chemistry as an analogy, because the siloxide is strongly nucleophilic and attacks the original molecule to yield the silyl ethahexamethyl disilocane, Me3Si, 2O. Conversely, while the SN2 reaction is mostly unaffected by the presence of a partial positive charge, plus, at the carbon, the analogous SN2 reaction at silicon is so affected. Thus, for example, the silyl triflates are so electrophilic that they react 108 to 109 times faster than silyl chloride S with oxygen-containing nucleophiles. Trimethylsilyl triflate is in particular a very good Lewis acid and ice used to convert carbonyl compounds to acetals and silyl enol ethers, reacting them together analogously to aldol reaction. 81. Cy-C bonds are commonly formed in three ways. In the laboratory, preparation is often carried out in small quantities by reacting tetrachlorosilane, silicon tetrachloride, with organolithium, grignard, or organoluminium reagents, or by catalytic addition of Cy-H across C=C double bonds. The second route has the drawback of not being applicable to the most important silanes. The methyl and phenyl silanes. Organosilanes are made industrially by directly reacting alkyl or aryl halides with silicon with 10% by weight metallic copper as a catalyst. Standard organic reactions suffice to produce many derivatives. The resulting organosilanes are often significantly more reactive than their carbon congeners, readily undergoing hydrolysis, ammonolysis, alcoholysis, and condensation to form cyclic oligomers or linear polymers. 80. Silicone polymers. Structure of polydimethylsiloxane. The principal component of silicones. The word silicone was first used by Frederick Kipping in 1901. He invented the word to illustrate the similarity of chemical formulae between pH2SiO and benzophenone, pH2CO, although he also stressed the lack of chemical resemblance due to the polymeric structure of pH2SiO, which is not shared by pH2CO. 80. Silicones may be considered analogous to mineral silicates, in which the methyl groups of the silicones correspond to the isoelectronic O of the silicates. 80. They are quite stable to extreme temperatures, oxidation, and water, and have useful dielectric, antistic, and antifoam properties. Furthermore, they are resistant over long periods of time to ultraviolet radiation and weathering, and are inert physiologically. They are fairly unreactive. but do react with concentrated solutions bearing the hydroxide ion and fluorinating agents, and occasionally, may even be used as mild reagents for selective E-syntheses. For example, Me3Si2O is valuable for the preparation of derivatives of molybdenum and tungsten oxyhalides. Converting a tungsten hexachloride suspension in dichloroethane solution quantitatively to WOCl4 in under an hour at room temperature, and then to yellow O2Cl2 at 100 degrees Celsius in light petroleum at a yield of 95% overnight. 80. Occurrence. Olivine silicon is the 8th most abundant element in the universe, coming after hydrogen, helium, carbon, nitrogen, oxygen, iron, and neon. These abundances are not replicated well on Earth due to substantial separation of elements taking place during the formation of the solar system. Silicon makes up 27.2% of the Earth's crust by weight, second only to oxygen at 45.5%, with which it always is associated in nature. Further fractionation took place in the formation of the Earth by planetary differentiation, Earth's core, which makes up 31.5% of the mass of the Earth, has approximate composition Fe25Na2Co0.1s3. The mantle makes up 68.1% of the Earth's mass and is composed mostly of denser oxides and silicates, an example being olivine, MgFe. 2SiO4, while the lighter siliceous minerals such as aluminosilicates rise to the surface and form the crust, making up 0.4% of Earth's mass. 82. 83. The crystallization of igneous rocks from magma depends on a number of factors, among them are the chemical composition of the magma, the cooling rate, and some properties of the individual minerals to be formed, such as lattice energy, melting point, and complexity of their crystal structure. As magma is cooled, olivine appears first, followed by pyroxene, amphibole, biotite mica, orthoclase feldspar, muscovite mica quartz, zeolites, and finally, hydrothermal minerals. This sequence shows a trend toward increasing complex silicate units with cooling, and the introduction of hydroxide and fluoride anions in addition to oxides. Many metals may substitute for silicon. After these igneous rocks undergo weathering, transport and deposition, sedimentary rocks like clay, shale, and sandstone are formed. Metamorphism also may occur at high temperatures and pressures, creating an even vaster variety of minerals. 82. There are 4 sources for silicon fluxes into the ocean include chemical weathering of continental rocks, river transport, dissolution of continental terrigenous silicates, and through the reaction between submarine basalts and hydrothermal fluid which release dissolved silicon. All 4 of these fluxes are interconnected in the ocean's biogeochemical cycle as they all were initially formed from the weathering of Earth's crust. 84. Approximately 300 to 900 megatons of aeolian dust is deposited into the world's oceans each year. Of that value, 80 to 240 megatons are in the form of particulate silicon. The total amount of particulate silicon deposition into the ocean is still less than the amount of silicon influx into the ocean via riverine transportation. 85. Aeolian inputs of particulate lithogenic silicon into the North Atlantic and Western North Pacific Oceans are the result of dust settling on the oceans from the Sahara and Gobi Desert respectively. 84. Riverine transports are the major source of silicon influx into the ocean in coastal regions, while silicon deposition in the open ocean is greatly influenced by the settling of aeolian dust. 85. Production. Silicon of 96–99% purity is made by reducing quartzite or sand with highly pure coke. The reduction is carried out in an electric arc furnace, with an excess of CO2 used to stop silicon carbide, SiC, Chrome accumulating SAD Smiley 27, CO2 plus 2C Psi plus 2 Co.
Yes, we have 2 Dennis videos. I need to put public. And of course, I not understand most of this. I don't have a university degree in computer science, or in chemical science. I have basic chemical from high school level, but I not remember much of that. Yes, I have 2 Dennis videos. They are public, then I need to add it to my read lists. Good. Let's continue. Yes, let's do it ready, but I think the camcorder run out of power. So let's, I think I'll take some candy now, but I will record. Let's do a short video on Dennis. Just do a video, 2 minutes Dennis. Yes, now something wrong with the memory cards. It's always like this. This is why I have to start my camcorder like this. I have to take it in and out. SD card error. Of course, it's been in and out many thousands of times. It's not working. God lørdag eftermiddag. Jeg optager video på engelsk her. Men jeg har lige sagt, at jeg skal lige lave en video på 2 minutter på dansk. Der er en chat slik der, så lad os lige lave en skål slik. Og det her kamera bliver tør for strøm lige om lidt. Lad os gå det klokken er 1:15. Jeg skulle egentlig lave varm mad, der er nogle gulerødder og sådan noget. Man kan godt gøre begge dele. Man kan både spise slik og gulerødder. Men lad os spise det sidste slik her. Mens jeg læser det der lidt kedelige, ikke kedelige, men jeg forstår ikke så meget af det. Så lad os spise det nu. Vi uploader lige senere. Jeg sidder og optager en video på engelsk her. Jeg har sagt på engelsk, at jeg lige skal bruge 2 minutter. Så må du da en pose slik fra Lidl i går. Så lad os spise det. Så bare sådan en lille kort video. Yes, just a short video. So let's go back with this camcorder, upload this later. It's soon 2 p.m. That's a little bit candy. That's a little bit, that's amino chloride. So that's licorice. That's wine gum. But silicon is a very important chemicals in a computer.